Hey everybody, this is a 10x Talk from Analytics. We're an engineering firm that writes medical device software.
Each Wednesday, we discuss a technical article or video. Sometimes people give talks and we record them. This is one of those recordings. We hope you enjoy it.
The title of this talk is Modern Cybersecurity Practices. It's a very broad title, obviously. I'm not going to cover everything that goes under modern cybersecurity practices, applications to medical devices. I just picked this so that we'd have a common place to start at. I'm actually going to talk about something pretty specific. It's about a software stress testing technique called fuzzing, and we'll get into the details later. But basically, it's a very effective way to find security vulnerabilities, other logic bugs, and a whole host of other things in memory unsafe languages like C and C++ code typically, but it's also being used in Python and Java. It's mostly for finding other types of bugs. They're not finding buffer overflows in Python and stuff like that, but it's being used there too. So when I say cybersecurity, I could be talking about just about anything. I could be talking about the IT side of things, what a system admin would do. Be talking about cryptography, about AES cipher suites. Be talking about web security. Lots of medical devices have a web interface that you can use to interface with the device, or in some ways lets you provide input to the device. That's a potential attack vector. There's the legal and compliance side of things. What is it that you have to prove to the FDA for you to be able to market your device as secure? There's the human factor side, like if your end user is a physician who doesn't know what cryptography is, then you wouldn't want to give them this control panel of all these options. They're very likely to make the incorrect decisions there. But I'm not going to be talking about any of those things. I'm going to focus on what I've called fundamental vulnerabilities. This isn't, at least not that I know of, an actual technical category, but I've just lumped everything that are more just like things that shouldn't happen anymore, given how long programming has been around. Stuff like buffer overflows or race conditions, or like use after freeze in C and C++ code. Yeah, so we'll get into all of that, but just to put a little bit more, I guess, meat on how dangerous some of this stuff can be. So I came across our MOD database, and for anybody that doesn't know, MOD is this database of incidents that happen with medical devices. And so if something happens with a patient and the doctor is using a medical device, they're obligated to report it here so that we can learn from it and track it. But I found this on our MOD alerts page at mod.analytics.com, so there was a problem with an infusion pump. And an infusion pump is it has a computer that mixes up a concoction of drugs before it gets put into the patient. And because of a buffer overflow issue, so you can see buffer overflow highlighted there. I just searched up buffer overflow, and this was one of the first ones that came up. Because of a buffer overflow issue, the infusion pump just stopped working. It crashed. And so the patient, in this case, they needed those drugs to survive, and they didn't. So the patient actually died. That's obviously really terrifying to think about, but it's even more terrifying that there are 5 or 6 other cases just like this one with just a quick search of buffer overflow. And if you search for things like virus or malware or a whole bunch of other things, there's even scarier stuff. So there's a lot of good reason to be investigating this area. Another example that's not from the medical devices field, but one that's just as consequential, is this is something called the Heartbleed Bug. So in 2017, Equifax, the financial data company, lost about like 3 to 4 million of their users' data because some hackers exploited Heartbleed, which is the name of a security bug, and a whole bunch of other bugs. And they didn't know about it for quite a while. So this was a really big security breach that cost a bunch of different companies, not just Equifax, a ton of money. And Heartbleed, so this just because they should be interactive. Does anybody know what Heartbleed is? Just by a show of hands. Okay, does someone want to take a stab at explaining it?
I can if you want.
Yeah, go for it, Matt.
Correct me if I'm wrong, but there was an addition to SSL where in order to keep a connection alive, you would send a payload plus the length of the payload as a structure. And there wasn't a check to see if I sent you just a short payload, but say 32,000 as the length, that it's guaranteed to fulfill the RFC. I think I don't remember the RFC offhand, might have been 6540. And the way that you could exploit this was you could ask for more memory than is allocated for that string, and eventually, after some repetition, you might be able to come across some of the private keys held in memory.
Yeah, no, that's perfect. So that's exactly right. It's based on the Heartbeat protocol, which is specified in RFC. And the Heartbeat protocol it's pretty simple. There's a server and then there's a client. The client sends a heartbeat request to the server, and it also sends a sequence of bytes that it calls the payload. And the server's job is to just return that same sequence of bytes back to the client, and then the client will verify that the bytes sent equals the bytes received. So it's just like testing the connection. It's a heartbeat. The problem, like Matt mentioned, is you can craft the heartbeat request in such a way that when you get back a request, or when you get back a response, you actually get more than just the payload that you sent, which is obviously really bad. So we'll actually I'll do that now. We'll actually go into the code and I can show you where this happens. Can everyone see my code?
Yes.
So I have a version of OpenSSL here, which has the Heartbleed bug, and I'm in one of their library files, and this is the culprit method. So if you look at what's happening, it's pretty straightforward. So they initialize some variables. I think the only relevant thing here is that they take whatever data the client gives them, and then there's a pointer p to it. And then in the RFC, it says that the first couple of bytes of the data that you get from the client is just the unsigned integer of the length of the payload. So you just need to read that as an unsigned integer, and that's exactly what this is doing. It's populating this payload variable with the first couple of bytes read as an unsigned integer. Then there's some other stuff that doesn't really matter. And there's these two code paths. So you can either be requesting a heartbeat, or you can be getting a response. There's nothing interesting happening in the response. So in the request, what happens is you allocate a new buffer, and the buffer is the same size as the payload plus some padding. And then all it does is it mem copies whatever it got from the client. So this is the same payload that we read from the client, and then copies payload number of bytes from that onto this empty buffer that they just allocated. And then it sends out the data, and then there's some cleanup. So that's basically the Heartbeat protocol. It's pretty simple. The logic is pretty straightforward, but there is a bug here. Does someone want to point out what the bug is, if they've already found it, or if they have a guess as to where it might be?
Seems like you could just write whatever number you wanted in the beginning, and you would get a buffer of that size back, even if the payload was big.
No, exactly. Like this is just such a blind mem copy. Like whatever unsigned integer you get is what it will assume the size of the payload, the actual payload is. So when you're just copying whatever client data, so the client could say, I sent you 1,000 bytes. Really, they only sent you 8 bytes. This mem copy will just continue copying past whatever, like past the 8 bytes, and we'll just copy whatever is there. If you're unlucky, it could be, like some confidential data, like the certificate. It's very likely that it could be just the certificate used, and that's obviously awful. So Yeah, so just keep this in mind. We'll come back to this later when we do a quick demo of fuzzing, but yeah, so we'll come back to this. So that's Heartbleed. So what is the remedy for stuff like this? And for stuff like this, I mean anything that falls under like memory issues or like use after freeze, just stuff that you typically find in C++ code that just shouldn't exist anymore. What are some typical remedies for stuff like this?
If you're lucky, you can find it statically.
Yeah, static analysis. That's a good first thing to do. Anything else? So one thing that lots of people do is use sanitizers. So sanitizers are just they're dynamic testing tools, which just means you have to run the code for it to do anything. That uses compile time instrumentation. So just means when you compile your code, you pass in some other flags that add on some bells and whistles so that you can debug this properly. But sanitizers let you do a whole bunch of cool things. Probably the most popular and powerful sanitizer that finds most bugs is Address Sanitizer, which comes with most relatively new versions of Clang and GCC. But Address Sanitizer lets you find bugs that are about memory or address, just like basic bugs like buffer overflow. So if you have this integer array of 100 elements and then you try to access something outside of it, then you get you should get an explosion. And if you run it with Address Sanitizer, if you pass in this fsanitize address flag, when you compile it with Clang and then run it, then you'll get, then it'll tell you. So Address Sanitizer can also help you find, I'm just going to run through these sanitizers very quickly because I want to get to the fuzzing, but each sanitizer is obviously complicated. There's a whole bunch of parameters you can play with. And yeah, it's worth diving into if you're into this stuff. But it also helps you find stuff like use after freeze. So if you create an array, delete it, and then try to return an element inside of it, run that with that Address Sanitizer, it'll catch it. There's Thread Sanitizer, which catches race conditions. It does some other things too, but race conditions are the most important things that it finds. So if you have a thread, this Lambda function, set this local variable x to 42, but then in the main thread, you're setting it to 43. That's a race condition. There's no mutex guaranteeing exclusive access to this variable. So, and if you run that with Thread Sanitizer, you'll find it pretty quickly. There's Memory Sanitizer, which lets you find stuff like this, where if you've initialized an integer array, but then haven't, for example, initialized it to 0, as far as the compiler is concerned, that's an uninitialized value, and it doesn't know what could be there. So it'll warn you about stuff like that. There's Undefined Behavior Sanitizer, which in my experience hasn't been all that useful. It's like if you've ever run ubsan on any of your code, you'll find that you'll get a ton of noise, most of which doesn't really matter. Some of which does, but most of it's just like it's not conforming to this C++ 17 standard or something. It's mostly just noise. Sometimes it's helpful. Most of the times, in my experience, it hasn't been. So what's wrong with sanitizers? Why is it that they didn't catch Heartbleed or stuff like Heartbleed as soon as they did? Does anyone have any guesses? So yeah, go ahead.
Well, it seems like sanitizers can't catch input issues, right? It's like the same problem of blindly accepting user input on a web form. You just don't know what you're getting.
Yes, yeah, I think that's basically the main reason. I think it's like it depends so much on how good you are at coming up with like test cases for your unit tests. So like if you point your sanitizer in the right direction with the right input, it'll find your bug. But you still have to come up with the test case that finds the bug. And that, like your developers do their best to come up with a relatively comprehensive test suite, but chances are you're probably missing a whole bunch of stuff. So the good news is you can do better. There is something called fuzzing, and fuzzing. So from the article I sent is a introduction to fuzzing. It's not exactly what I'm going to talk about, but does someone want to try to define fuzzing or their understanding of it from the article?
Like randomly sending data to an application to see how it handles it?
Yeah. That's exactly it. It's just providing random input to a program trying to break it, and then recording when it gets broken. Just right off the cuff, that sounds like a really stupid thing to do because the space of all possible inputs is a lot larger than the space of inputs that will cause your program to crash. So it doesn't really make sense to just randomly throw stuff at it, hoping it'll break and hoping you'll discover something interesting. In the very beginning, when fuzzing was just getting started, it was a really stupid thing to do. And then they weren't all that successful. So fuzzing research, I think nothing really interesting happened for quite a while. I think now in the literature, they refer to that as dumb fuzzing or monkey fuzzing. But now it turns out you can add a whole bunch of bells and whistles to that idea of generating random input and providing it to a program and make it really, really effective at finding hard to find bugs like the Heartbleed bug. So just to compare testing from fuzzing, when you write unit tests or any sort of test, you have some API that you want to test. You provide it with inputs like input 1, input 2, input 3, and then if you have the test case, like if your test case covers all the stuff that you want to cover, then good. If not, then you're missing a whole bunch of stuff. Fuzzing is different because in this really simplistic model, you're just running an infinite loop and generating new test cases, and then passing that into your API and seeing if it will break. So that's the only difference. I just usually think about it as generating test cases, and so it's pretty, like, you can use address sanitizer or any of the sanitizers with fuzzing. You're just getting a lot more test cases. So there's random fuzzing, which I talked about, where it's a pseudocode. You generate some input, you execute it, you try to break the program. But then there's also coverage guided fuzzing, which is what really works. Random fuzzing doesn't really work unless your input space is really tiny. With coverage guided fuzzing, the basic gist of what happens is you compile your code with some specific flags. Then you choose a random input from a corpus. So you have a data set of input files that are pretty, it's like a training set. In a machine learning model, you have a corpus of stuff that you initialize let's say the weights in your matrix with. This is something that's like an analogous thing. So if you were trying to test a JSON parser, your corpus would just be a bunch of JSON files or things that look like JSON files. It would have files that are non-binary with curly braces and quotation marks. So it would pick out a random input from the corpus. It would mutate the input somehow. And this is where different fuzzers set themselves apart. This is also where you can apply some machine learning, but you can generally do quite well without machine learning with just genetic algorithms that work really well. But yeah, this is a very complicated area, and there's lots of really fancy stuff that people do that usually goes way over my head. But you can mutate stuff. You can mutate the input, and then after you mutate it, you pass in the mutated input into your program. And because you've instrumented your code with some flags, when you run it, you'll actually be able to record how much of your code base you covered in each execution. So you'll have some metric of code coverage, and you can use that to guide your fuzzing. So say you execute this input, this mutated input, you record how much code coverage you had. this is just one metric, but if new code paths were discovered in this execution, then you could consider this a good data point, and you could add it back into your corpus, and then this would just keep going. There's also other stuff you can do, but code coverage, improving code coverage is a good metric. So you basically have this massive jungle of code paths, and you're just trying to find interesting areas, and the more code paths you can find, the more likely you'll find interesting bugs. That's the idea, at least. So that's coverage guided fuzzing. Is there anything else? Yeah. So now we can go back into
Just
this.
a quick question on the coverage guided fuzzing.
Yeah.
Like, is there like a gradient or something that the fuzzer follows? Like, how does it know that what it's doing is increasing the code coverage and like what to do next? You know, or is it just
so it's in the fuzzers that I know the details of, it's a lot more simplistic. It's just, yeah, you run this program with this input. If your code path metric increase, or your code coverage metric increases because you did this, then consider that a good input, and then just keep going.
Got it. Okay, cool.
I think there's fancier stuff you can do with it that probably works a lot better. The fuzzer that comes bundled with Clang, the lib fuzzer, doesn't have any of that. It has what I just told you, the very basic like metric.
Got it.
But yeah, so back to OpenSSL. We're going to try to find this line of code using fuzzing, and it should do it relatively quickly with respect to how long it took security researchers to find it, which is about 2 to 3 years. So let's try that. So the first thing that you need to do when fuzzing a library is to write something called a fuzz target. And the fuzz target is just it's the entry point into your fuzzing algorithm. So if fuzzing were just poking a black box from the outside and seeing what breaks, then the fuzz target is the black box that does the actual work. So this is what we're trying to break. This can be anything. Here I've just included the OpenSSL library. There's some library boilerplate here. And then the interesting part is this line here, SSL do handshake. So all this is really doing, this is the black box that we're trying to stress test. And all this is really doing is taking random data, which the fuzzer will generate, and then doing something with it. Here it's just directly populating the payload with it, but you could use this as a seed to a random number generator or something, or you could cut it up in different ways and like pick out unsigned integers from there. You could do anything. You just get this blob of data. You have to do something with it to test your API. So in this case, do handshake utilizes the Heartbeat protocol. So if there's something wrong with Heartbeat, we should be able to find it just by executing this API call. And this is the only thing that you need when you're running a fuzz target. You just need to write this one function called LLVM test one input. This is just a helper method. This is all you really need to get started with fuzzing. So let's try to compile that. So I have the broken version of OpenSSL, which I downloaded. Oh my God, you can't see that. But yeah, I have the broken version of OpenSSL there. So I'll just compile it. I just compiled it before the meeting, so this will be pretty fast. But when you compile it, you'll want to compile it with Clang, because Clang has fuzzer built in. And you'll want to pass in the debug flag. And you also want to pass in address sanitizer, so fsanitize address. And this is what I was saying before about how you could use fuzzing and sanitizers in a complementary fashion. There's no part of this is doing any fuzzing. This is just instrumenting the OpenSSL library with address sanitizer and getting it ready for fuzzing. So we'll run this.
Would it be
Yeah.
possible to increase the font size a bit? I don't know if
Oh,
it,
yeah. Sorry. Can you see it?
great. That's great. Awesome.
Yes. Okay. So sorry, nobody probably saw that, but basically you compile it with Clang, you pass the debug flag, and then you also pass in the address sanitizer flag. We're just preparing libSSL for fuzzing. So after you run that, you'll want to compile this fuzz target with Clang, and I already have that, so I'm just gonna. So all this is doing is it's compiling our fuzz target again with the G flag, the debug flag. It's passing in address sanitizer and then this other option called fuzzer. And this is what libfuzzer, they just call it fuzzer, but the backend algorithm is called libfuzzer. So you pass in this flag, you add libSSL and libcrypto libraries, include path, and then this executable that it outputs is what does the fuzzing. It's the infinite loop that keeps running, trying to randomly generate things until something breaks. So that's basically it. Once you have all of that, you should just be able to run this new target that you've created, and then you should just be able to let this run until it finds interesting things. I'm not going to let it keep running because when I first let it run to find Heartbleed, it took about 2 hours. We're not going to wait 2 hours for that. So I'm just going to stop it. But trust me, it'll find it. In a couple of hours, you'll get something that looks like this. And it tells you address sanitizer found a buffer overflow on address, blah, blah, blah. You know, on the Heartbeat OpenSSL method on line 2586. So if we go back to the library here, line 2586 is the mem copy. So that's where the buffer overflow happened. And it found that in 2 hours. If I had more cores on my VM, you'd probably find it in less than like an hour, probably less than 30 minutes. But you know, I think a lot of large companies just run this on clusters continuously. So I know Google has a project called OSS Fuzz where they just take projects that are part of the global internet infrastructure, stuff like curl and like gzip and you know, all these just integral libraries, and they fuzz those in their giant cluster of virtual machines. And every single day they find tons and tons of bugs, and then they report the bugs to the maintainers. And then yeah, and then they do pretty well. So the other thing about Google is that they also run fuzzers inside of their company. And I think I saw a stat that said that like now 80% or 80 or 70% of the bugs that are reported internally are just bugs found by fuzzers, at least in C and C++ code. So this fuzzer is just like churning out memory overflows and heap overflows, stuff that developers would have a hard time finding. Some of it is probably noise, but like 70, 80% is still, including noise, a very, very, very respectable number of bugs to find just automatically. Okay, so I think that's all I wanted to say here. Does anybody have questions about that example?
I have a question. When you ran this, did you find anything besides this?
I did not. This is the only thing I found. I think this is also after they'd run libfuzzer on OpenSSL, at least the patch that I'm running. So this one is a pretty contrived example. I think they basically made it so that Heartbleed could be found very quickly, so they could show off the power of fuzzing, but then not much else. So, but like I know recently somebody gave a talk at C++Con where they fuzzed random libraries that had a certain amount of stars on GitHub, and somebody fuzzed some like JSON parsing library, and like this is like very widely used and lots of, I'm sure, used in the medical space and also other very critical software spaces, which is what makes it more concerning. They're just like littered with buffer overflows that are trivial to notice and also trivial to fix, but just weren't caught up until that point. So it does work. I think in this case, I didn't find anything because OpenSSL was probably well tested at this point with fuzzers. But yeah.
Yeah, the difficulty there is if you have 7,000 bugs, you have to kind of have a judgment call for each one to see if it's exploitable, right?
Yeah.
That was my experience running with OpenSSL.
Yeah, yeah. If you've got a ton of bugs, it's definitely hard. But so in my experience with fuzzers, the number of bugs that you can expect is, unless your library is really bad, is probably on the order of, if you run it continuously, maybe like one or two a day, or something like that. So like it wouldn't be like 7,000 unless you had a really, really bad library, Yeah, okay.
So I had a couple of questions. I don't know if now's the right time, but if you could go to the pseudocode for the fuzzing, I want to just see. So I guess my understanding is the what's it called? Like the assembly, the checker. So that's what's just telling you that, hey, we found the bug, and then your code just runs random stuff, but there's no assertions, or I guess
No.
exception or something. It would.
Yeah,
but
that's a good point. You can add assertions like you would in test cases here. Most people just try the assertion is just, will the program crash? Will it like sigint or sigabort? But yeah, you could put assertions in there too.
Yeah, I see. That makes sense.
So is it true that usually most of this fuzzing happens at like a really big black box level? Like it seems like you could take a white box approach where you fuzz every single function. It's kind of like a unit test.
Yeah.
But that would require a lot of implementation knowledge about what that function is.
Right.
Does most fuzzing happen on the black box level?
Yeah, it mostly happens on very high level API functions that do a whole bunch of different things. So it's probably more similar to an integration test than it is to a unit test.
Got it. Cool.
Yeah. Okay, so just keep going. I think the only other, so this is, now that fuzzing has become very popular, there's this comic that I think most people have seen where somebody says, get back to work, and the person says, I can't because my code is compiling. Now, I think there are plenty of people who just say that their code is fuzzing instead. I just put this on here because fuzzing is not obviously a silver bullet. You still have to have some like knowledge about your code base to be able to point things. You can't just call a very simple API method and try to break like an addition function. This is totally pointless. So you still have to have some knowledge about your code base to be able to use this really powerful tool well. And the other thing is there's a whole bunch of stuff you can catch with unit tests much, much faster than fuzzing. So this doesn't mean you should just not write unit tests or integration tests. Fuzzing is just going to catch weird bugs that you would never think to test of. But the bugs that you can't think to test of, you should probably do that with unit tests, because you'll have a much clearer error message in case something breaks. You're not going to have to like dig through this giant log of address sanitizer, stack trace, whatever. You'll just get something really nice like this assert failed or something. So fuzzing is not the answer to everything. Yeah, I think so. I think only the last couple of things that I wanted to mention is that fuzzing is used in large companies to find lots and lots of bugs. There are tools that do fuzzing for languages other than C and C++. So instead of memory overflows and memory and like thread issues, you would find just logic bugs. So maybe you have like assertions in somewhere, and it would just find code paths that are likely to trigger logic bugs. I'm not too well informed on how fuzzing happens in Python and Java, but I do know that companies are doing it and doing it well. OSS Fuzz is the project by Google that I was telling you about. And then don't need to run fuzzing all the time. Most of the fuzzing infrastructure that I've seen does run it all the time. So they'll just have something connected to their continuous integration pipeline where they have this VM running fuzzing all the time. And anytime they push changes, the binary gets updated, and they just keep running the fuzzers. And if and OSS Fuzz and other tools actually do something even beyond that. If they find a crappy input, if they find a test case that results in a crash, they'll go a step further and try to minimize the input to its smallest possible crashable input. So they don't want to give you this massive sequence of bytes like, yeah, this causes a bug, but when you test it, it actually takes you 5 hours to run it. They'll give you something they'll try to make it much more manageable. That's one thing people do. And yeah, I think that's all the stuff I wanted to cover. This is so fuzzing is not a silver bullet. It's usually very expensive because you'll have to run it on a cluster. But stuff like Advanced Sanitizer and memory sanitizer and thread sanitizer, that stuff is kind of the first step to fuzzing. So I think the very least that most people can do if they're writing C and C++ code is run their unit tests with these sanitizers enabled, because chances are you'll probably find something unless you've been very careful. And the next step after that would be to just run fuzzers for a little while on some simple, easy to black box API functions. And you don't have to run it on a cluster. You can just run it on your machine for a couple of hours, or like put it in into some CI pipeline that runs it for a little while. It doesn't have to be terribly expensive to be effective. So yeah, that's basically it. If anyone has any questions about anything, I can go back and answer them.
This is a great presentation. Thank you for going through this. I really enjoyed it.
Good. Okay. Awesome. Thanks. Appreciate it.
So I do have one question. So you obviously you mentioned several times that memory unsafe languages. So for instance, with Rust, a lot of those parameters that are normally being tested by fuzzing are, if not, they're not impossible, obviously, because you can always have unsafe code, but they're trying to be designed out. But do you think that fuzzing still provides value even in languages that have those safeguards in place?
I think it provides the same value it would provide to like a language like Python or Java, where it's much less likely to encounter like memory bugs. Like logic bugs can still be found using fuzzing, where you can just, it's just a way of generating unit tests. It doesn't necessarily have to result in a buffer overflow or something like that. I don't know if it would be as useful. You probably wouldn't be as effective in finding bugs at the same volume as when you're running it on a C library like OpenSSL. But I think my intuition says you'd probably be able to find something. But yeah, in many ways, Rust is really the answer to a lot of these problems.
It seems like putting in a bunch of assertions or exceptions for like invariants would make fuzzing on memory safe code more likely to find logic errors.
Yeah.
Like if you're writing it, it's like, oh, there's no way that could happen, but just in case, like, well,
exactly.
And then maybe later on, it turns out the fuzzing finds some way.
Yeah, I think that is what I have in mind too when running on memory safe languages. That's a good question though. I think there's some work being done on Rust. I'm not really too sure, but I think like in the worst case, because this is all LLVM based, you can find some way to run it on most languages that use LLVM in some way. So like I'm sure Rust has something.
I like the idea of including assertions for invariants. I know another type of bug that I've run into on some of our projects that involve processing data, usually from cameras and so on, is like divide by zero bugs, or like bugs where like you have some sort of data analysis pipeline, and you probably testing with a handful of sample data sets, and like certain numerical operations just can't happen that way, but you don't necessarily think like, oh yeah, what if these two things just happen to be the same and it divides out? I don't know.
Yeah, yeah, it'd probably be useful there too. I think I think with all of these, like fuzzing definitely has a cost in terms of just time it takes to find stuff, and you have to like, it's pretty easy to build out to integrate fuzzing into your code base, but it is work. So like in some cases, it might not just might not be worth the effort to do this kind of stress testing. I think it's also worth keeping in mind, but like generally, it's pretty easy to integrate.
I really enjoyed this presentation, and I was also thinking about the way that fuzzing might be used on like mobile apps, especially with Android being C++. And I'm curious if, I haven't really read into it much, but I'm curious if you saw anything about some of the vulnerabilities that fuzzing might catch in a mobile app.
To be honest, I'm not really sure. I know like I'm like very uninformed about Android or mobile development, but I think Java has a pretty popular fuzzer that does some stuff. But even like stuff like OpenSSL, like those libraries are getting called from everywhere. If they're getting called from, they have like Java wrappers that call them and Python wrappers that call them. So vulnerabilities found in C and C++ code that are used everywhere would be useful, like even with mobile devices, I'd imagine. But yeah, I mean, I think I don't really know too much about the mobile space in fuzzing.
Thanks. Yeah, it was a pretty vague question, but thank you for the answer.
Sure.
Yeah, definitely. Thanks a lot for the presentation. I learned a lot from this. I think some of the practical takeaways for me is like in 62304, you want to kind of divide out your software system into various software units. And one of the main reasons for doing this is you can assign a different risk category to these software units, class A, B, and C. And the type of testing you do and the type of code review and that kind of thing could be different for each of these software units. And I'm thinking like anything that's software level C, which, these things could include things that are life critical, like for example, the bug that you found with the infusion pump. There's probably some critical path there that perhaps if a software unit was identified as being class C, that you would not only not only on top of unit tests and all the other testing, but also run fuzzing on that as well.
Yeah, I think that's a good takeaway. Knowing how important like reliability and like knowing where stress testing matters is a good step to take first before doing anything else.
Another thing that jumps into my mind is like, I think thinking about this data analysis pipeline issue again. Like I would imagine that if you're fuzzing where your input is an entire image, that like the probability of, if it would take way longer just because the dimensionality of your input's so much larger to run into a bug. So like figuring out where to like, what part of your program to like set the input at to increase the likelihood of, yeah.
Yeah, it's definitely tricky. The most common use case for fuzzers, not surprisingly, are stuff that's very easy to black box, but also not extremely high dimensional. Like you're not processing like volumetric images. The like stuff like compression algorithms, like parsers. Parsers are probably where they're used the most because there's tons of bugs to be found in parsers. And then the input doesn't really have to be that complicated for you to trigger a bug. But I have seen something with some image processing library that uses fuzzing. I forget what it was called, but I think it's out there somewhere. Yeah, but modeling. So I think this is the other point about you can't just throw fuzzing at everything and make it work. There's a decent amount of work that you have to do ahead of time to model what it is that you want to fuzz, and like in some ways that's the hardest part if you have a problem like the image one.
I'm curious, if fuzzing could also be used to discover bugs in machine learning models. Like there are all these, different explanations of bugs where if you alter like one pixel in an image, suddenly it goes from cat to hot dog or something, or those kinds of things. Kind of a systematic corpus-based fuzzing approach to kind of detect those kinds of conditions more rapidly.
Yeah, I bet you could use the same like genetic algorithm, like mutating of input, that type of algorithm to find something. Yeah, I mean, I feel like that's a useful use case. Like just outside of finding crashes in like NumPy or TensorFlow, just finding stuff that makes you give weird, like make you predict weird things would be interesting.
Yeah, definitely.
Like a confidence step, if you
Yeah.
look through every pixel and say this is a 89% of this ensemble comes out hot dog. This is an 89% hot dog. When you mentioned the monkey fuzzing, I guess I hadn't heard that term before. I wonder if that's related to the Chaos Monkey project, like that came out about the same time as fuzzing. This is kind of like a similar idea where you decide to disable a node on a network and see if your whole network has a problem functioning. So it's kind of like a distributed systems approach to fuzzing, kind of live.
Yeah. No, I could be. Is it around? I don't know. Actually, I think, when did fuzzing come out? In like the 80s or something? Is that around when Chaos Monkey?
Oh, am I wrong? I didn't know it's from the 80s. Wow. Okay.
I think so. I could be wrong, but I think this was like, I think there was a paper that came out in the 80s, and then no one touched fuzzing for like 20 years. So really, it probably started much later. But yeah, I guess it could be from like the monkey term could be from that. I also think this picture is wonderful. Okay, yeah, I think that's it then. I can so I put a link to the slides. There are there's links, there's source links down at some of the slides. CPPCon, C++Con has, if you look at the talks that have been given in the last couple of years, a lot of them are about fuzzing. So fuzzing is definitely increasing in popularity in the C++ community and the C community. But C doesn't have a conference, so they just talk about it in CPPCon. But there are references here, and this GitHub repo in particular has a whole bunch of other stuff, cool stuff too. There's also another, yeah, so there's this long one. This is a PowerPoint that some guy did about fuzzing, which has a whole bunch of other stuff that I didn't go into. There's other types of fuzzing. They also go into libfuzzer, what exactly it does, AFL, which is another type of fuzzer, what it does. So in case anyone wants to dig into those.
Let's have a quick question about this slide. We're on it. So on the right, like the coverage guided, is it true that the two steps that require kind of like manual fine tuning up front is the choose random input and the mutate input?
So yes, the random input one, the mutate, the only manual intervention that's necessary is to pick your fuzzer. So
okay.
If you pick libfuzzer, that's kind of decided for you.
Okay.
But yeah, random input, That's definitely the hard part, because you might have an API that's wonky and hard to test with just a raw sequence of bytes. So you'll have to do something. You have to like cut up the byte somehow to make it meaningful before passing it to your function. But yeah.
Got it. And are there tools that can help you form that corpus? Like maybe there's some runtime instrumentation that you can add.
I think so. I think you can. I think with Clang's libfuzzer, you can actually just like give it some noise or random data, and it'll try to like once it finds a bug, it'll. I don't know exactly how it works, but it does give you an output directory full of random sequences of bytes, and you could use that as a corpus. Most of the time, I think the recommendation is to manually craft it so that so you start off at this like a solid base.
Got it. Yeah, it's kind of a tricky situation because you're trying to find something that's unknown,
right?
But you need to kind of read between the lines in order to find that.
Yeah.
And if you knew enough about it, you just write a unit test. Like if you knew there was an error condition, you'd write a unit test. So it's like it's kind of tricky.
It's more like just pointing it in the vague right direction. Like with for example, with a JSON parser, you don't want to have binary blobs as your corpus. You want to have like ASCII characters and stuff that a regular JSON file would get, because it wouldn't make sense to just test a JSON parser with an XML file or something. So just like narrowing the stuff, but yeah, I mean, like you could definitely point it in the wrong direction if you just have a corpus that doesn't have a wide enough scope or something.
Yeah.
So like in the case of the JSON, would you start with a corpus where like maybe you would have a number of valid JSON files?
Yeah, so the corpus doesn't have to be stuff that crashes your program. It just has to be some place to start.
And then I see, so then it'll mutate it, execute it if the coverage increases. So like maybe it like just added a letter to one key. It'll say, oh, okay, like, and this made the software do something different. So like by kind of giving it that starting point, it more like, I see.
Yeah, it's giving it some sort of structure.
Yeah.
It's a pretty cool field.
Can it get so say that like with the JSON parser, you had to delete 2 quotes in order to go from what was a string to now it's an integer. Like could it, like this is kind of like an optimization problem. I guess it could get stuck in some sort of local optima. Does that happen with these input mutators?
Honestly, I don't know enough about the mutators and how they work to properly answer that, but there's probably some workaround, is what my intuition says, but no, don't know.
Cool. Yeah, it's just very interesting stuff.
Yeah, I think so too. Okay, yeah, I think that's it. Thanks for listening and for the questions.
Great. Yeah, thanks so much, Mima. This is great.
Thanks, Bimba.
Yeah, sure thing.
Hey,